Hi Pre-Calc, we are in our vector unit and we are dealing with some vector application problems, specifically the ones that deal with work, which are the easier ones, and the ones that deal with an airplane and the effect of the wind on that plane's path and its speed. So those are a little bit more challenging, and we're going to look at those a little bit here. These are extra practice problems I gave you for the night before your quiz. Number 1 here says an airline's navigator determines that the jet is flying 560 miles an hour with a bearing of north 40 degrees west. But the jet is actually moving at 455 miles per hour in a bearing north 35 degrees west. What is the velocity of the wind? The first thing I want to do is I want to take these directions and I want to turn them into a directional angle where we're going from the positive x-axis. The way we tend to measure angles always in trig and pre-calc is starting at the far right, and that's our 0, and going counterclockwise. So let's look at this. North 40 degrees west, that's this one right here. Okay, so north is up here. So north 40 degrees west is basically saying 40 degrees west of north. In other words, we're going north, but we've been blown off course by 40 degrees toward the west. So this. So that I am 40 degrees west of north. That's the idea here. Okay? Now, if that's what I am in terms of these particular bearings, which is with compass headings, great. This is my vector. Now, forgetting about the whole north, south, east, west, I'm going to convert those to a directional angle where 0 is over here. And this is what we always want to do. 0 is at the right, and we are measuring counterclockwise, meaning I'm turning counterclockwise from 0. So in other words, I'm spinning, here's 0, 30, 40, 50, 60 degrees, 70 degrees, here's 90. So this would be 90, this would be 180, and this would be 270. And this is in the system we want to go with. So if we're trying to figure out what the directional angle of this is, then to get there, I'm going, let's see, 90 degrees through the entire first quadrant. I have to turn through the entire first quadrant, so that's 90, plus another 40 degrees right there. So I've got 90 plus 40, so this whole angle, I'm going to go ahead and connect it, is 130. So that's the direction for this north 40 degrees west, is 130 degrees. So that's right here. So that's 130 degrees. Next, let's go ahead and look at north 35 degrees west. Well, it's pretty much the same thing, except this is 35. So now we're 35 degrees west of north. So if I come from over here, I'm going 90 degrees through the entire first quadrant, plus another 30 degrees, 35 degrees, excuse me. 90 plus 35 is 125. So the directional angle of this vector is 125, or the positional angle is sometimes what it's called too. Sometimes it's called the rotational angle. But basically it's all talking about we're rotating from 0 is due east or straight to the right on the positive x-axis, and then we're going counterclockwise. Okay, so now I don't even care about those old descriptions at all. I just know that I have a jet that is flying 560 miles an hour at 130 degrees. Now I'm going to change that into a vector in component form. The vector is 560 cosine 130, comma, 560 sine 130. And it's always the same. Magnitude times cosine times the direction. That's the horizontal. Magnitude times sine times the direction is the vertical. Okay, and I'm sorry this is so shadowy. I was trying to make it a little brighter by turning off all the lights in the room, so you're getting all kinds of spooky shadows, so sorry about that. All right, let's look at the next thing it talks about. That was the 130. That says a jet is flying, blah, 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 blah. But it is actually moving. Okay, so what this is saying is if we take the jet's path and the speed of the wind and the direction of the wind all into account, the final result is what we have right here. So the actually moving is telling me this is your result. So this is the resultant vector. Okay, so actually moving is telling me the result. It's actually moving 455 miles an hour at 125 degrees. So as a vector, in component form, that's 455 cosine 125, 455 sine 125. Okay, so I have the speed of the jet, like in terms of what the pilot is trying to fly it, and then I have the actual result of what's happening after the wind acts on the jet. And remember, the jet, in other words, the original jet speed, if this stands for the original, like the speed of the jet with respect to the air around it, plus the wind, gives me the result. Okay, and another way you could describe the result is with respect to the ground. Okay, in other words, what's actually happening in the world in terms of this jet. So if I have this one and I have this one and I'm supposed to be finding the wind, I'm not going to be adding, I'm going to be subtracting. Just like if it said 5 plus x equals 10, to get x I would do 10 minus the 5. So in other words, the wind speed is the resultant vector, or the wind vector is coming from the resultant vector minus the original, the jet's original speed and angle. Okay, so here's the resultant, here's the jet, and I failed to bring a calculator over here, which is just great. So I'm going to subtract this one minus this one, the result, which is the final, minus the jet. All right, so I've got to first subtract the horizontals, basically subtract the like things, subtract the cosine expressions and subtract the sine expressions. So I've got 455 cosine 125 minus 560 cosine 130. Okay, and when I do that, I get 98.98. Then I'm going to do this result, the vertical component of the result, minus the original flight path of the jet, or the plan, anyway, before the wind starts blowing it off course. 455 sine 125 minus 560 sine 130. Okay, this gives me negative 56.27. Remember that since these angles are given in degrees, you want to be in degrees. Okay, now I didn't actually ever draw the situation, so let's look at this and see if this makes sense. Okay, my jet is going at 130. Actually, let's go ahead and use the grid. Sorry if I made you dizzy. The jet is going at a direction of 130, which is over here somewhere. It's not exact. Magnitude of 560. This is what it's trying to do. Okay, here's what it ends up doing. 125, and I realize they're not that far apart, but I'm trying to give space to show what I'm doing here. 125 degrees, so this is 125, and 455. And I'm sorry, that's not degrees. I don't know if I can erase it without messing up my line. I don't think I can. Okay, there we go. 455 is the magnitude of this vector. So this is the original jet. This is like if the jet were not affected by the wind at all. This is the final result after the jet's affected by the wind. Okay, and remember the jets plus the wind equals the result. So that means my wind is doing this, something along the lines of this. Okay, well, we got in component form 98.98 and negative 56.27. This is right and this is down, which makes sense because this is going down and to the right. So my vector for the wind is indeed going down and to the right. It does make sense in the context of the problem. And I'm ready to finish this up. Here's my initial point. I'm going right 98.98, down 56.27. This is the vector I'm trying to find. Now I'm going to find this angle right here, but remember that what I ultimately want is the angle all the way around from due east. This is my 0. I'm going to go all the way around from there. But I'm going to find this angle to help me figure that out. Inverse tan of 56.27 over 98.98. And that will give me 29.6 degrees. So this is 29.6 degrees. So this is 29.6 degrees below the x-axis going to the right. Okay, now if we are below the x-axis going to the right, that means we're over here. So 29.6 degrees below the x-axis. Remember, the x-axis is 0, but it's also 360. All right, so we've got all the way around. Now let's get rid of this. Starting at 0, going around to get to this. This is going to be almost a complete turn. It's only 29.6 degrees shy of a complete turn. So I do 360 minus 29.6, and I get 330.4. So that is my angle. So 330.4 is my direction for the wind. How about magnitude? Sorry, it's kind of tilted there. All right, magnitude. We've got basically Pythagorean theorem. Square root of 98.98 squared plus 56.27 squared. So let's do that. And I get 113.86. Not the most realistic problem ever, because a wind speed of 113.86 miles per hour, I mean, I guess it might exist, but usually hurricane force winds are like 70 to 80 miles an hour. So I am pretty sure that no plane would be in the sky under those conditions. But that's how we do it. All right, next. Number 2. Actually much easier because of partially where it is and partially the fact that I don't have to translate the directions. It says it takes off in the direction of 56 degrees. Okay, so let's go ahead and look at it on the grid. 56 degrees is in the first quadrant. So this is the direction. Helps people see the paper. And it counters a wind which is blowing to the northwest. Okay, it doesn't say from the northwest. It says it's blowing northwest. So that means it's going, here's northwest. It's blowing toward that. Okay, so I'm going to start here and I'm going to go that way. Now what is that? That is 45 degrees above this line, or you could say that's 135 degrees from over here. Okay, and we want to measure our angles from 0 over here. So this is what I've got going on. This one has a speed of 375, or a magnitude of 375, which reflects the speed, and the wind is 35. So that would really be a lot shorter than that is, but you get the idea. Let's make it a little shorter. Okay, so this time it's asking me to find the resulting speed and direction of the jet. So the nice thing is I don't have to work backwards on this one. I just want the resultant. I'm finding the resultant. Last time, remember, we had the resultant and we were trying to find the wind. So here is my J for jet speed. Here is my W for wind speed. And here is my R for resultant vector. Okay? So I'm going to take the jet speed and direction and write that in component form. 375 is the magnitude times cosine 56. 375 is the magnitude times, whoops, I write cosine again, sine 56. This should say sine. All right, now the wind. And this one is very straightforward. We're just adding. 35, and we said that was 135 degrees, and 35 sine of 135 degrees. Now, how do I know this one's straightforward? How did I know that I'm just adding here? Well, you're using this equation either way. It's just that what we were missing in this problem meant that we had to subtract. This time we have J and W, so we're just adding. Okay? So and J could be, you could have A for airplane, but the point is the plane plus the wind is going to give you your result. So J plus W equals the resultant vector. And so I'm adding these. So they're nicely set up for me to just add top to bottom. And I've got 375 cosine 56 plus 35 cosine 135. And that gives me a horizontal component of 184.95. Then for the vertical, I have 375 sine 56 plus 35 sine 135. And I've got 335.64. Okay, so that's my horizontal, my vertical component. We already drew the picture here. So let's go ahead and figure out this vector. See, once you get here, you're just figuring out the magnitude and direction of this vector. None of the rest of it matters. It's like someone just gave you a vector and said, find the magnitude and direction. So we have 184 to the right. And I'm sorry I didn't show this. Here's where I'm starting. I'm going 184 to the right. Then I'm going 335 up, and this is definitely not proportional, but it doesn't really matter. And I'm trying to find this angle. This is my vector. The theta is always right there by the initial point of the vector. So I'm going to do inverse tan again of 335.64 over 184.95. And I get 61.14 degrees. That's right here. And because that's pointing up and to the right, that's in the first quadrant. So this is 0. So I'm rotating 61.14 degrees. So this is actually my direction. I don't have to add or subtract it from 180 or anything like that. And finally, my magnitude is the square root of 184.95 squared plus 335.64 squared. Pythagorean theorem, same as the distance formula. And I get 383.22, and it's miles per hour, I think. Yeah. There we go. Number 3. A commercial airliner has a velocity with respect to the air of 420 miles per hour, and its bearing is 220. The wind at the altitude of the plane is blowing from the northwest, blah, blah, blah. Find the velocity of the plane with respect to the ground. Okay, so velocity with respect to the air means this is basically your speed if there were no wind. Okay? This is your speed. This is the plane's basic speed, not accounting for wind. Velocity of the plane with respect to the ground means accounting for wind. Okay, now we're taking the wind into account. Okay, so first off, this one has bearings. Okay, remember bearings starts straight up. Let me move it over. Why is it not showing? Yeah, I guess it is. Okay. Here's 0, and we go this way. That's bearings, which means this would be 90, this would be 180, this would be 270, and this is 360 all the way around. Okay? If they tell me that the bearing is 220, that's between 180 and 270, somewhere here. 220 is 40 degrees bigger than 180. Okay, we're turning this way. And it's 50 degrees less than 70. Okay, so I'm 40 degrees from here and 50 degrees from here. Those are things I can figure out while still thinking in terms of bearings. Now, when I'm changing that to a directional angle or a positional angle, basically it's like I erase all the stuff about bearings and now look at it again. The vector is still where I figured out it was when I was thinking in terms of bearings. It's just that now 0 is over here, and I'm turning this way. So this is 90, this is 180, and then we are going 50 degrees past 180, so this is 230. Okay, so that is my positional angle. Is 230, so I'm just going to take this and I'm going to change it to 230, and now I don't have to worry about that anymore. All right, so this is the airliner. Let's call it a plane. I don't know, let's call it an airliner. My airliner is going 420 miles an hour at a direction of 230, which means 420 cosine 230, 420 sine 230. Okay, now the wind is blowing from the northwest. Okay, so still thinking this is the kind of angle I want, remember, with 0 over here. Northwest, I just have to figure out. It's not already in bearings, it's just talking directionally. If it's blowing from the northwest, then basically it looks like this. Okay, it's blowing from the northwest means it's blowing to the southeast. So, in terms of figuring out where that is, 0, 90, 180. This is 270. I can keep going. Now, southeast is right in the middle between 270 and 360. So this is 45. This is 45. So basically, I'm 45 degrees less than 360, which is 315. So that is my direction of the wind. So the wind, 315. All right, so W is 50 miles an hour at 315. So 50 cosine 315. 50 sine 315. Now this is the plane, this is the wind. We put those two together to find the resultant, which is with respect to the ground. This is like the true direction of the jet, the true speed with respect to what's happening on the ground. I'm putting these two together. It's just like J plus W, it's A plus W. I just used a different letter. So I'm adding these. So basically just like the last problem. So I've got 420 cosine 230 plus 50 cosine 315. This gives me negative 234.62. For the for the vertical component, I have 420 sine 230 plus 50 sine 315. And that gives me negative 357.09. Okay? So I'm going to, well, let me just point out, we never really talked about what this picture looks like, so let's do that. If the plane is heading at 230, this is 230, and its magnitude is 420. And then I have the wind heading, here's my horizontal, so here's my 0 all the way around here to 315. So this angle here is 315. And this one has a velocity, of 50 miles an hour. Then remember that 50 is actually much shorter than this. So it's going down and to the left. Here's where my resultant is going to be. That makes sense because I got negative, negative. Negative, negative means go down, go to the left. Left first, down next. So I'm starting out, here's my initial point for the vector, go left 234.62 and down 357.09. Now you notice I'm not putting the negatives because I'm just thinking of this as a right triangle and figuring out using right triangle trig that my inverse tan, or my theta, is going to be my inverse tan of 357.09 over 234.62. Did I say 234? Oh, I'm sorry. Yeah, 234.62. This is 56.69 degrees, right here. 56.69 degrees. All right, so let's think about where that is. 56.69 degrees, we're pointing down and to the left. My triangle looked like this, so this was 56.69 degrees. So if we're starting over here at 0, we're going all the way around 180 plus another 56.69 degrees. So 180 plus 56 plus 6.69 degrees is 136.69 degrees. That's my direction. My magnitude is going to be the square root of 234.62 squared plus 357.09 squared. And that gives me 427.27. So that's 427.27 miles an hour. Okay, magnitude, direction. This looks exactly like the last problem, and it is. I'm sorry. So we don't need to do that one because it's just a repeat. Now I did want to point out to you, don't forget these work problems, but they're super easy. Work is the force times the distance times cosine of theta, where theta is the direction in which you're doing the work. Okay, so force here is 30. So it's basically you're just literally plugging in. So 30 times, here's the direction, so it's cosine 35, and the distance is 40 feet. So this is literally all you're going to do to get this answer, is multiply those numbers out. So we've got 30 times 40 times cosine 35, and that gives me 982.98. Now what are my units? Foot-pounds. Okay, we have pounds and feet. These are foot-pounds. Next, a mover exerts a horizontal force of 20 pounds on a crate as it is pushed on a ramp up pushed up a ramp that is 10 feet long and inclined at an angle of 25 degrees above the horizontal. Okay, so again, so force, 20. Distance, the ramp is 10 feet long. Angle is 25. So we have 181.26 foot-pounds. And again, that's my answer. Hope this helped. Sorry it was so long.